response of the system, the transfer function analysis, and the PID tuning process of a TCB board. I'll compare an untuned versus tuned response and explain how the final controller values were chosen. So we have me, Alex, John, Marco, and Michael and Boro on this presentation today. And in our next slide here is an open loop response. This is the open loop response of the system here. No feedback or control is applied, so the plot shows how the system naturally reacts to a step input. We can see that the system rises slowly and gradually approaches steady state. Analyzing the curves helps us understand the natural behavior before adding a controller, and it gives us the key values like the time constant and steady state gain. Right here is our transfer function calculations. These are the calculations used to estimate the transfer function slope. It took the difference in output values and divided it by the difference in time, giving a slope of approximately 1.119. That slope value is what I plugged into the PID tuning formulas. And this is the transfer function given from that. This plot represents the system's transfer function response. The curve shows a smooth exponential rise that levels off around 110 to 115. This confirms that the system behaves like a first-order dominant process. Understanding this shape is important because it determines how the PID controller needs to be tuned. This right here is our slope values. To tune the controller, I needed the slope of the response curve. Using 2 points on the graph, I calculated the change in output and the change in time, which gives us this line slope. This slope is crucial because it becomes the value of m in the Ziegler-Nichols style tuning formula, so the step directly feeds into the PID gain calculation. And this is our slope calculations for the PID. And using the tuning equation, I calculated the proportional, integral, and derivative gains. So the initial untuned values were 0.17, 0.014, 0.536 of KD, KI, and KP. After tuning, the final PID gains became 0.17, 0.008, and 0.536. The main adjustment was decreasing the internal gain. This reduces integral windup and removes oscillation. So right here is our PID closed loop untuned. Here we see the closed loop performance using the default untuned PID values. There's a clear overshoot and slow settling time. The system oscillates before stabilizing, which tells us the control is not well balanced. This untuned behavior is exactly why the PI needs adjustment. And in the next slide, we tuned it. And as you can see, the TCB tuned. This hardware responses with the same untuned PID gains. Again, we see overshoot, noticeable oscillation, the peak happens early, and the system takes time to settle. These results confirm that the default controller settings are not acceptable for stable and accurate control. And once we closed loop it, after tuning the PID gains, the closed loop response improves dramatically, overshoot is reduced, and the response becomes smoother, and the settling time shortens. The tuned controller stabilizes the system faster and tracks its set point much more accurately. And after we've tuned it, we can see that our results are somewhat the same. Now this is the real hardware, so this is the actual TCB board. The output rises more gradually, and without aggressive overshoot, the oscillation is significantly reduced and the system settles pretty smoothly. This clearly shows that the tuning process improved both stability and precision. And to summarize all this, the open loop response helped identify the system's natural behavior, and we calculated the slope to estimate the transfer function parameters. Using those values, we computed the initial PID gains, and the untuned PID shows overshoot and oscillation. So after tuning the system, it became a lot more stable and a lot smoother, and overall the tuning process resulted in a well-controlled, stable system. Thank you guys for listening.